piezoresponse force microscopy, since that's somewhat of my background. I just wanted to start by showing some of the broad range of things that we can do with AFM. I happen to be in a bio institute, and my talk is mostly focused on nanoscale materials or functional materials. But AFM can be used for imaging mechanical properties of living cells. It can be used for high-speed imaging at very high resolution of myosin motor proteins walking along actin tubules, actin filaments. And in something very probably dear to our hearts at the moment, it's being used quite recently to look at SARS-CoV-2, so our COVID-19, both for doing rupture events to measure the force interaction between the spike protein and receptors that are normally on the cell, also for imaging SARS-CoV-2 and doing nanomechanical measurements of SARS-CoV-2. More relevant to our work, and again, this is a paper just from the last couple of weeks, looking at hexagonal boron nitride. You've probably seen some papers where there are some moire patterns with other 2D materials, including graphene. And then in this particular work, they're using a technique called electrostatic force microscopy. And in the EFM phase image, so here's the topography, you can see that there's 4 layers here, 8 layers, and 12 layers here. So some, and with some rotation between them. But within this EFM phase image, there's quite some interesting contrast, including these triangular domains. So what I'd like to talk about is how do we go from AFM, which I'm going to introduce, to types of electrical measurements like this, characterization of nanoscale materials. So the basic outline for my talk, I'll be discussing the basic principles and overview of AFM. I mean, I hope AFM is familiar to everyone here, but just in case there are people that aren't familiar with it, this will be a very basic introduction. Then I'll start going into some more specifics and details, talking about electrical modes, and in particular, piezoresponse force microscopy, where I'll go into some detail of the history, the basic principles, mechanisms for single signal enhancement, as well as spectroscopic modes. And then in the second half, I'll be talking about some recent research results from my group, including the use of PFM, conducting AFM, and using the AFM tip to nanomechanically machine surfaces and carve out nanostructures. So AFM, as you probably know, goes back to the introduction and invention of STM. And the very first AFM was actually built using STM as the detection mechanism. And they used a diamond tip glued onto a gold foil. And we'll come back to this diamond tip again, because that's what we were using for doing our nanomechanical measurements. So you can understand that the interaction between the tip and the sample is very important. And the mechanism for imaging materials properties, whether it's topography or some functional property, all comes down to the size of this tip and the interaction force between the tip and the sample. And here's a picture of somewhat of a modern AFM, where we have the laser bouncing off the cantilever into a photodetector or a position-sensitive detector. And that's how we're using this optical beam detection method to measure the surface topography, but also the interaction forces. As I mentioned, so STM was the initial scanning probe microscope that we'll be talking about. And it was invented in 1982. Already in 1986, the Nobel Prize was awarded for the invention of the STM. And that's the same year that AFM was invented. And there's been quite a lot of development in the preceding years, in the subsequent years, and this only goes up to the last decade. We'll be talking about PFM, which was kind of invented around 1992. Now, here's again this basic schematic diagram of AFM. We'll have a probe with a cantilever, and at the end of the cantilever, we have a tip, a sharp tip that in principle goes down to a single atom. The laser bounces off the cantilever. Every time the cantilever deflects, we can detect that change in position by looking at this photodetector, which is tracking the position. There's 2 basic modes for AFM. We have contact mode and an amplitude modulation mode. In contact mode, you can see the cantilever is here tracing out the surface of the sample. Every time the cantilever deflects, there's a feedback loop engaged that adjust the tip sample separation to keep the force constant, to keep the deflection constant, to keep the bending of the cantilever constant. So you're imaging with a constant force, dragging the cantilever along the surface. You can imagine that there's normal forces and torsional forces involved in this. And so contact mode can be detrimental to very soft samples. Intermittent contact or amplitude modulation or tapping mode, as it is commonly called, operates something like this. So the cantilever is vibrated often at its resonance, and then you're tracking the amplitude of vibration, the amplitude of oscillation of the cantilever, and you're trying to keep that amplitude constant. So the tip starts out far away and is vibrating. As it gets closer and closer, that amplitude is changed, usually reduced as it gets closer to the surface and starts tapping the surface. And then you're trying to image at a constant amplitude, and you're adjusting the tip sample separation to keep that amplitude constant. And in doing so, you can again map out the surface topography. Contact mode AFM is often, contact mode AFM can be used also with a conducting cantilever. And so while we're in contact with the surface, we can be measuring conductivity or current. Contact mode is what we use for piezoresponse force microscopy, and we saw some nice examples of PFM in the first lecture by Dimitri this morning. With amplitude modulation and other dynamic modes, that's where we would use techniques like EFM and scanning Kelvin probe or Kelvin probe force microscopy. And the development of AFM can be traced even back a little bit further, because what we're interested in as microscopists is, imaging a surface, feeling the interaction forces in a way, or finding a way of measuring some kind of functional property. So I'll point you to this 1929 paper on the report of an optical lever profilometer. So you probably are familiar with some kind of profilometry, the idea of kind of taking a stylus and dragging it along a surface. And I think what's interesting is in the development and improvements of this profilometry microscope, they started noticing that there could be unstable probe bending of this stylus as it was dragged across the surface. And they actually introduced I guess in the 50s, in 1950 or so, a piezo activation. So they started, in essence, tapping, vibrating the profilometry stylus to be able to have more stable imaging and minimize the type of forces that might be detrimental that we see in contact mode AFM. So in a way, this is a precursor to the dynamic AFM methods, such as tapping mode or amplitude modulation that we just talked about. And I'll point you to this paper as well. So this is kind of an early microscopic measurement of magnetism, and you can see, or you can probably imagine that you're seeing some magnetic domain contrast in this image, and it's a bit like magnetic force microscopy that we have today with AFM. So I'd like to show this schematic, this diagram, to kind of show how the different AFM modes or scanning probe modes fit together. So STM, as we talked about, what you're doing is you're applying a bias and measuring the current, and that's very similar to conducting AFM, CAFM. You're applying a bias and measuring a current. With normal AFM, with contact mode and tapping mode or intermittent contact or amplitude modulation, you're applying a force and essentially measuring a displacement and using that to map out the surface of the material. And PFM and EFM and Kelvin probe force microscopy all fall kind of at the intersection, the diagonal of this schematic. Here you're applying a bias and you're measuring a displacement. So the bias that you're applying will create some kind of electromechanical or electrical force on the cantilever. That displacement is then measured by the AFM. So there's a wide range of techniques for measuring functional properties by AFM. We talked in that opening slide about doing local mechanical measurements. I'm not really talking about that today. I'm going to focus more on electrical characterization, but certainly magnetic characterization is possible as well. In this case, shown here as a lift mode technique, which is a common way of doing Kelvin probe force microscopy as well. And these electrical characterization techniques can span from conducting AFM to EFM, Kelvin probe, scanning capacitance, and additional techniques as well. And they're often used for characterization of functional materials. And I'll probably start talking about electromechanical characterization and ferroelectric characterization in the upcoming slides. And here are some books, not very recent ones, but the idea of using scanning probe microscopy for functional characterization goes back to the inception of these techniques, and you can find more information in books like this. Okay, so with PFM, what we have are, ideally, we're measuring short-range electromechanical properties, short-range electromechanical measurements. So we have a conducting cantilever in contact with the surface. We're applying voltage to the tip. The AC voltage is what's used to measure the electromechanical deformation. The DC bias might be applied, say, to offset an existing contact potential difference, or to apply a bias such that you're switching a ferroelectric material or looking at the bias-dependent electromechanical properties of the material. And so you can see that if you're applying the bias, the AC signal to a piezoelectric material, you'll induce some deformations. But you also have these long-range effects, and these long-range forces due to the electrostatics, the whole probe is conducting, and so you basically have a capacitor, you have non-local probe effects, and you also have the force directly on the cantilever itself. So you can already start to see a similarity between this local kind of PFM electromechanical measurement and the longer range electrostatic measurements of EFM and Kelvin probe force microscopy. There are many different methods for doing EFM and Kelvin probe, but one of them is a lift mode or an interlead mode. So you first measure out the surface topography doing your amplitude modulation or your tapping mode, and then you specify a lift height, and you basically retrace that surface. You're always the same distance, and when you're the same distance from the surface, the forces that you're measuring are just going to be these long-range forces. And if you don't have a magnetized tip, only a conducting tip, and you don't have magnetic domains in the surface, then these long-range forces are going to be electrostatic. And so basically these equations will explain the electrostatic force. So the force will depend as a function of distance, the voltage applied, and the capacitance gradient that you have owing, say, to the geometry of the probe that you're using. That voltage that's present can relate to the contact potential difference between the metal coating of the tip or the conducting tip and the surface you're looking at, whether it's a metal or semiconductor. And so you can apply a DC bias to offset that CPD, as I'll explain in a second. But you're also applying this AC signal. So you can imagine that when you're doing PFM, you're also measuring some kind of long-range electrostatic forces. But if the PFM signal is strong, that can dominate the long-range electrostatics. If you expand this force by plugging in this voltage, you can see that you have several different components to the force. Normally what you do with Kelvin probe force microscopy is you look at this term using a lock-in amplifier and you try to minimize it. And by minimizing it, and this is basically the electrostatic force that you would normally measure also with a lock-in amplifier, but you try to minimize this force, and if you find the DC bias that is equal to the contact potential difference, basically this term is minimized. And so you can make a plot, a map of the DC bias that minimizes the contact potential difference that minimizes that force. And so you have a map of surface potential or contact potential difference. That's a closed loop technique where you have a feedback loop to minimize that first harmonic of the force, but there are some other approaches as well. If you're interested, we can talk about it later. Another contact mode electrical technique that I'll be talking about today, mostly at the end when I'm talking about my own research, are these conductivity measurements, so CAFM. In that case, you're applying a bias and you're measuring the leakage, say, through the material, through the film thickness, but you can also have configurations where you have some electrode and you're measuring a lateral, an in-plane conductivity or a current. So now I'll talk a little bit about PFM. And as I mentioned, we had some nice images this morning already. And I'll take this back to the beginning from these early papers up to kind of some recent history. So hopefully you can see it's not too small, but this is actually kind of the first scanning probe measurement of piezoelectric activity. Those of you that work with ferroelectric materials, and this happens to be PVDF, as we heard from Vladimir earlier in the workshop. And you can see this normal kind of hysteresis loop, this ferroelectric switching. And in this 1990 paper by Burke et al., they used STM, so STM to measure it. And so the history of PFM can be traced to these first local studies of local bias-induced sample deformations in piezoelectric materials using STM, but also using scanning acoustic microscopy. And so that's this paper here. Again, we're investigating the piezoelectric properties of PVDF. So the history of PFM is traced to ferroelectric polymers. So you can see the setup here. You can see again mapping the surface, but also generating local switching loops. And the researchers, it's basically some of the same authors in these first three papers, and they claimed that they were interested in improving the resolution for the STM-based method and the acoustic-based method wasn't quite high enough. And so they developed a scanning probe, kind of AFM type based method with a metallic tip. And you can see the local domains that they switched again in a PVDF film. And so this is really the first PFM paper kind of as we see it now. It has all the same components of kind of modern day PFM that we do, including local ferroelectric loop switching. So it's really nice. I think it's highlighted over here. The local piezoelectricity has been measured by other techniques, but the resolution wasn't satisfying, and so they implemented this mode. Okay, so that brings us kind of today to today, and so now it's about 30 years of piezoresponse force microscopy. I'm happy to share these slides if people want these references, and you can just contact me by email. But PFM was first demonstrated in '92 to probe the local coupling between electrically biased probe and resulting mechanical sample deformation in a ferroelectric polymer PVDF, using approaches to study using scanning acoustic and tunneling microscopy. And then shortly thereafter, several groups kind of across the world were using PFM to study ferroelectric materials. And some of those papers are listed here. So from '94 to '96, we have some of the earliest PFM papers, and we start applying it to different materials, including PZT. And it's this paper here by Grooverman, where it's, I believe, the first paper where they start referring to it as piezoresponse. So this is kind of the first piezoresponse force microscopy paper, but you can see that the technique goes back a couple years before that. And my journey is a bit shorter, but I do have a paper that goes back 20 plus years. So my story is a little bit like 20 plus years of piezoresponse force microscopy. We had a paper that I'll talk about later that came out last year. Okay, so the basics of PFM, I've already kind of explained it, but we're applying a voltage to the tip, and that's going to result, if the sample is piezoelectric, it's going to result in a cantilever deflection or torsion due to a sample deformation. So the sample deformation might be in plane or out of plane. And if the tip is in contact with that sample surface, as the sample expands, the tip in contact with it will also deflect or twist if there's an in-plane motion. And that's what's shown here. And so it's the piezoelectric effect in a piezoelectric sample. This can happen, and as has been alluded to, if you're applying a bias to a functional material, there can be other origins of tip deflection or torsion, and so it's always something to be aware of. Basically, what we have is that an AC bias is applied to a conducting probe in contact with a sample. The sample expands and contracts with the bias, and the deformation is detected by monitoring either the cantilever deflection or torsion. And this animation here from NTMDT highlights it nicely. So you probably can't see it, but the cantilever is kind of vibrating up and down as it goes over these domains. And so the idea is that your oscillation frequency, your modulation frequency is much higher than the scan rate. So you're getting a lot of oscillations per pixel as the cantilever is scanned. You saw that it was vibrating up and down here. And as it goes here, you can see that the cantilever is twisting. And so you're able to pick up the twisting of the cantilever and map out both in and out of plane domains. So you can end up with images like this, where you collect all at the same time, the topography, the PFM amplitude, the PFM phase, where you can collect the mixed signals, so the amplitude times the cosine of the phase. The amplitude has information about the local piezoelectricity. And the phase has information about the local domain orientation. So this could be an in-plane, an out of screen domain, or an into the screen domain, for example. And if you collect data both for the out-of-plane deformations and the in-plane deformations, you can in principle reconstruct them to create kind of a vector PFM map, where the color here would denote the orientation of that piezoelectric ferroelectric domain. Okay, and PFM, of course, can be used for a wide variety of applications, from imaging to patterning of ferroelectrics, to studying domain dynamics in ferroelectrics, to doing local switching spectroscopy studies, as we'll talk a little bit about. You can do measurements as a function of temperature and other parameters. As we'll see later, you can do measurements as a function of tip pressure as well. So one of the things that comes up with PFM is that we're trying to measure really small displacements. The piezoelectric coefficients are often on the order of picometers per volt, and so you're always trying to look for ways to enhance the signal without causing some other problem. So an obvious way to enhance the signal is just to apply a larger bias. But if you're working with thin films, the higher bias might cause dielectric breakdown. You might be damaging the sample. Another way to enhance the signal is to operate close to the contact resonance of the cantilever. When you're doing AFM, I mentioned for tapping mode that we have a resonance of the cantilever owing to its mechanical properties and geometry. So the cantilever will vibrate really well at a certain frequency. In contact, that normal resonant frequency of the cantilever is shifted by a factor of around 4, depending on the loading force. And so in contact, you also have a contact resonance. And so if you want to operate your PFM close to the contact resonance, you'll have a enhancement factor equal to the quality factor of the cantilever. So you need to know this transfer function of your cantilever of your detection system. One of the drawbacks of operating on resonance in AFM is that you can end up having quite a significant shift in this contact resonance owing to different mechanical properties. Say the stiffness is different, so the contact stiffness is different, or just owing to the changes brought about by different tip sample contact areas due to the roughness of the sample, for instance. And this shift can lead to crosstalk. This isn't a very good example of crosstalk, but you can see here that there is some topographic influence on the PFM. And if you operate close to the resonance, and this is a relatively smooth surface on the order of a couple nanometers in roughness, and other samples that we look at might be much more rough, and this shift in the resonance can be quite high. So operating single frequency on resonance is what a lot of people will do, and it's okay, but you have to be careful because if you're close to the resonance, you'll end up causing yourself some problems. In particular, the phase contrast will invert as you're scanning. So some of the methods for enhancing this while avoiding the problem. So the single frequency approach I described as having a little bit of an issue, but often you can operate, say, at the shoulder of the peak, and as long as the peak shift isn't so big, then you won't have huge problems in some kind of crosstalk problem, but you would have some issues, say, in your amplitude. You'd have regions that have high amplitude and low amplitude that are more related to the topographic crosstalk or the phase shift or differences in mechanical properties than they are to differences in electromechanical properties. Two other approaches are some kind of resonance tracking approach, as I'll explain in the next slide. But basically, you're trying to stay on that contact resonance, and if the contact resonance shifts a little bit, you're still staying on top of it. Another approach to operate on resonance is called band excitation, and here you can see even from this time domain of the signal, the frequency is changing. So basically, you apply a voltage that excites around the entire resonance. So you're picking up that range of frequencies around the contact resonance. So as long as it stays within that band of frequencies, then you collect the entire spectra, and then you can plot data as needed, as you like. So the resonance tracking approach, basically, so here's the example of this contact resonance. Here's an example also of the phase signal in blue inverting if the resonance shifts too much. And in this approach, what we're doing is sending two AC signals and trying to operate one of the frequencies on the left side of the peak and the other on the other side of the peak, and employing a feedback loop to track that resonance. So always looking and making sure that if the peak is symmetric, you're right on the opposite side of the peak in both cases, so you can track it even if it shifts. And with that technique, you're able to stay on the resonance and collect data. And that data might look something like this. So here you can see the topography. Here's the PFM amplitude and phase. Since we have 2 data points on either side of the resonance, we can fit the data to extract the quality factor and the resonant frequency as well using a simple harmonic oscillator model. Bend excitation can do all of that as well, and it has the advantage, I suppose, of not requiring a feedback loop. Anytime you have a feedback loop, it can introduce some issues. With band excitation, then you just have to make sure that you're exciting that entire band of frequencies so that you always have the full resonant frequency within it. And you can see that both are somewhat equivalent in terms of the data that you can acquire. So now we'll talk a little bit about spectroscopic modes. And of course, you can do spectroscopy with conducting AFM and other techniques as well. EFM, as a function of DC bias, will allow you to determine the contact potential difference. But here I'm focusing primarily on piezoresponse force microscopy. And with piezoresponse force microscopy, when we do spectroscopy, we're typically looking at ferroelectric materials, and we're looking at the switching properties. So you could think of a ferroelectric as having a spontaneous polarization that you can change the direction of. I'm sure many of you in this audience are familiar with that. And so what you can, in principle, envision is that you're using this as some kind of memory element or memory state where you have a binary 1 or a 0. So this waveform is basically designed to kind of slowly creep along until you start to nucleate a domain, then keep going until you saturate and come back and switch in the other direction, as is shown here. So we have the DC bias. On top of the DC bias, we're applying an AC signal. That's our detection, and the DC bias is our switching bias. So we're building up a hysteresis loop in doing so. So you can see for a small bias, maybe nothing happens. At some point, we nucleate a small domain. That domain might start growing across to the other side and growing laterally, since we have this electrode of a certain size with the tip. And then eventually we might start nucleating an opposite domain and eventually filling that in. So this is what piezoresponse force spectroscopy is, or switching spectroscopy, as you might have heard it called. Once you have this data, then you have to figure out how you're going to analyze it. You might be doing some fitting or just extracting data at particular points, or as has been exploited in the last 5 years or so, doing some kind of machine learning to look at the data. And so you're thinking of extracting out these parameters, and once you extract out the parameters, you can make a map of all the different parameters, and it can look something like this, where you're getting PFM, you're getting the nucleation bias, even the work of switching, the area underneath this curve. So there's a lot of data. It becomes quite a big data problem after a while, which is also exciting. Before I gave the example of DART PFM, this resonance tracking approach, and didn't really talk about about band excitation. Both band excitation and DART can be used for this kind of switching spectroscopy study. So you can operate on resonance, you can track the resonance, or you can at each of these bias on and off states, you can send your band excitation waveform, which contains a band of frequencies, such that you're generating the data and collecting the data across the entire resonance of the interaction. So there's the contact resonance shown there. This is the amplitude, this is the phase. You can see that here would be the switching events where the phase has flipped, because for that DC bias, that was sufficient to switch. And so you can end up getting switching spectroscopy data using band excitation as well, or as I said, with DART on resonance with resonance tracking. And we're not limited to just this type of waveform. There are any number of waveforms. You're only limited by your imagination, I suppose. So any number of waveforms to collect data, and here are a couple of examples. So this fork-like wave where you're slowly increasing the bias window, or a pund-like pulse waveform where you're doing a setting pulse and then measuring the switching as a function of pulse width or pulse voltage, depending on what you're interested in measuring. Okay. I won't go into any detail, but I do want to point out that in the last 5-6 years, a significant effort has been put forth into understanding your PFM signal, understanding the origin and the mechanism of the contrast that you see. And there really is a lot of nice work that's been done in these areas. And a lot of the technique development has been centered around trying to understand and determine whether or not you're measuring a true piezoresponse signal or an electrostatically influenced piezoelectric signal. So again, as I mentioned, I'm happy to share these slides. If you're not familiar with these papers, they're certainly worth looking at. And for further reading on PFM in general, there are a couple review articles from my group and some from other groups from the past. I think this one's probably, these two are probably the most recent, and they're certainly worth a look if you're working in the field of PFM and or are interested in learning more about PFM. So that concludes my introduction to PFM in general. And now I just wanted to talk about some more recent work from our group. And what I'm going to present was work performed largely by PhD student Fengyuan Zhang, who graduated during our first lockdown here in Dublin and is now a postdoc in China. And this work was supported by Science Foundation Ireland, and we had collaborators in China and in the US and in Northern Ireland for this work. And what I'd like to talk about for the next 20 minutes or so is work that we performed on bismuth ferrite. So bismuth ferrite, I think this is a 50 nanometer film. These are slightly two different films, sorry, but I just want to show the evolution, what can happen. So PFM can be measured at different forces, at different loading forces, and with tips with commercially available diamond probes of sufficient stiffness, you can generate quite large forces. In this work, we go up to several micronewtons of force. At relatively low forces, so around 50 nanonewtons, we would get our normal PFM image. If we apply slightly larger forces with mixed phase bismuth ferrite, we're actually able to change the structural phase of the bismuth ferrite. We can change the proportion of rhombohedral or tetragonal domains by applying a force. So first, we switch the material in one direction. You can note the topography here. And after applying a force, we change the topography, we change the way the domain structure looks, but we haven't switched the material, the ferroelectric. So we can have we start with a bias-induced tetragonal phase, and we can mechanically induce a mixed rhombohedral tetragonal phase when we're applying on the order of 400 nanonewtons, so a little bit higher than we would normally image our PFM with. And what I'd like to talk about in the next bit are these two results here. So measuring switching as a function of loading force and measuring current as a function of loading force. So when we push into the surface with a large force, we can measure the switching. And we can look at the evolution of both the coercive field or the nucleation voltage, as well as a switching related current. So you can see we didn't see a strong current at low forces. And as we go to increasingly higher forces, you can see that the magnitude of this current peak increases, but it also shifts a little bit to the left. I'm giving away the main experimental results already, but this is what I'm intending to talk about. So this shift in the current and the increase in the current peak. Now, if we apply an even larger force, we can actually carve out these really nice structures. I'm not sure if that translates well to a Zoom lecture, but hopefully you saw the cantilever animation and it was moving along, creating this pattern in the surface. And we were able to make quite nice patterns. This is a harp from the UCD logo, and then scratching a surface to create nanocapacitors. So that's what I'll talk about in the next few slides. Apologies. And so a little bit of the motivation for this work. As I mentioned, with ferroelectric materials, you can envision a ferroelectric memory where you have bits of ones and zeros for domains pointing up or down. And one of the ways for noting if a domain switched up or down is to look at the displacement current. That can be a switching current associated with the switching event. And as you go to smaller and smaller bits, to smaller and smaller elements, ferroelectric elements, you can see that the currents get quite small. So if this is 10 picoamps for about a 300 nanometer ferroelectric island or ferroelectric element. And you can imagine if you're going even smaller than that, higher density, you'd have a smaller size, a smaller current, and then it becomes very difficult to detect whether or not you have a switching event to know whether it's a 1 or a 0. Related to that, it's been noted that what can happen when you have a switching event is that you can have quite large currents associated with tunneling across the dead layer that is at the surface of a lot of ferroelectrics, some region that doesn't switch, but you can still end up tunneling across it, and that can lead to a much larger injected current than the normal switching displacement current, or switching or displacement current. And so these two things got us thinking, along with this idea that the dead layer at the surface can act as a series resistance and suppress the current, but the current across this dead layer has a term that depends on the thickness of the dead layer. And what if we apply a large enough force that we can, in essence, squeeze that dead layer, push or compress the dead layer a little bit, maybe then we can enhance the current a little bit further. So that's the basic idea, the experimental design. The question that we propose is, can decreasing the dead layer thickness increase the current? As we're applying a force, a larger force, does the dead layer squeeze become thinner? Does the current become larger? And can we detect a larger switching related current when the material switches? So that's what we were interested in looking at. So here is a schematic again of conducting AFM, measuring the current across the sample owing to the bias that we apply. So you can see this is a spectroscopic approach with conducting AFM. So we're applying a voltage and measuring the current. We can see an event at a positive voltage and an event at a minus voltage. And then this is kind of a leakage current associated with the asymmetry of the contacts. But we do see these two events that tend to happen around where we see switching. So we measure switching at the same time using PFM hysteresis loops. And we can overlap that. And we can see that the switching appears to be associated with these large currents. So when we switch is when we measure these large currents. Okay, so we can do a little bit of investigation. We can send a preset pulse, switch it in one direction and then switch it back and send several positive voltage after switching it negatively. And you can see for cycle 1, after the first positive bias after the preset, that's where we measure the current. And we don't see current at the other pulses. So this is clearly associated with the switching. Similarly, we can do it in the other direction. The preset pulse, the first cycle is when we see the current, and the subsequent switching, the subsequent pulses where we don't have actual switching, we don't see that current. So we identified it as a switching related current. And then we wanted to understand what happened as a function of tip loading force or pressure. Okay, so again, we start with a low pressure, so 50 nanonewtons, which is what we normally use for imaging for this sample. We don't measure a strong current. 100 nanonewtons, still maybe at the start, the onset of a current peak. And as we keep increasing, we start to see a sharper peak. So this is at 3.25 volts. As we go to higher and higher force, higher pressure, we see that the current is increasing, but also shifting to lower values. And so what we see actually is that the hysteresis loops, from the evidence from the hysteresis loops is that the coercive field is changing, as I showed in the preliminary slide. And so this continues to shift to the left. The switching becomes easier and easier with higher forces, and the current increases to the point where at 600 nanonewtons, the the film is already switching at just 2 volts and under 2 volts for 750 nanonewtons. And this was with increasing voltage, so increasing force, sorry. So we wanted to see if the opposite was true. So we can go from a high force to a low force. Do we still see this corresponding shift? And as we decrease the force, we do. So we can see that this shifts, goes back, lower voltage, a higher voltage and lower current. So it seems symmetric to an extent. And so since we have an idea of what the size of our tip is, we can calculate or estimate the polarization associated with this switching related current. And we can see that the polarization ends up being quite high, much higher than you would expect from bismuth ferrite. You can see the force dependence of it, and you can also see the shift of the switching voltage or the peak, the location of the peak as a function of force. So we have this nice symmetric response. And what we propose as an explanation is that what is happening is that we are actually squeezing this, and in squeezing the dead layer, in squeezing this interfacial layer, it allows both tunneling and it lowers the barrier a bit. So we think that it looks a little something like this. So that barrier becomes thinner, or the dead layer becomes thinner and the barrier becomes slightly lower. And that's what's leading to the increased currents that we see associated with switching. So we still have some work to do around this. We hope to really prove this effect. But it gets us thinking, what happens if we push harder? Do we get even more current? At what point are we going to damage the film? And even can we create structures? So we saw at the outset of this motivation, this introduction, that a 300 nanometer ferroelectric element had a 10 picoamp current when it switched. So can we actually use the AFM to create the nanostructure and then study the switching as a function of force? So that's the next part of my presentation. And just to put all of this in perspective, humans have for a long time been interested in tools and mechanical carving. You can see this early lathe from Egypt up to more modern machining tools. And in these machining tools, they're often using a diamond cutting tool to cut the workpiece or the sample, and even using AFM to look at the quality of the cuts that were made with the diamond cutting tool. And these days you can purchase single crystal diamond tips. So much like the original diamond tip for the original AFM that was glued onto a gold foil and used with STM as the feedback mechanism for the first AFM. So now we can have these nice sharp diamond tips. And so maybe we can use them to carve structures, and maybe we can use them to carve structures in ferroelectric materials. So it's a tool that has several names. So mechanical scanning probe lithography, nanomechanical machining, tip-assisted milling, nanosculpting. There's a variety of terms. It of course will depend on your choice of tip material and properties, the normal and torsional stiffness of the lever itself. You can combine it with imaging, but also tomography. So you can remove material as you're scanning, but also be measuring some other property. So you can measure PFM as a function of depth. You can measure current as a function of depth, and reconstruct the surface in kind of that 3D or Z-stack way. And it can be used for measurement of materials properties as you're going along. So you can measure the Young's modulus, say, as you're removing material. So you can have a simultaneous detection of the process as well, because you have the photodetector, so you can measure when you're applying a certain force and where there's a change in the force application. So there's a lot of applications, I think, for this AFM-based machining. And I guess we're kind of new to this game in a way, because a lot of people have already worked with nanomechanical machining. But we found that it hadn't been extensively applied to ferroelectrics. So it's been used to make silicon nanochannels, transfer a photograph or create a photographic representation on an aluminum surface, a polycarbonate nanoarray. Here's an example of tomography, so measuring current of a conducting filament as a function of depth and then reconstructing what you see. So of course, nanofabrication with ferroelectrics, or the idea of making nanostructures, is well studied, obviously, from this point of making high density memory storage, data storage applications. And people have widely used focused ion beam. And focused ion beam can be associated with damage, and the damage might need to be removed. One of the ways that damage is removed for some groups is actually to use an AFM tip to come and scrape away some of the gallium implantation. And mask-assisted pulse laser deposition as another example. Certainly there are some bottom-up assembly approaches, but these are the types of approaches that are used. And maybe there's scope, maybe there's an application where a nanomechanical machining method has some advantage. So we wanted to explore that. Ion injection may limit the minimum nanostructure size. Here, the shape and dimension of the mask might limit the minimum nanostructure size. In AFM, you might speculate that the tip size, the tip shape, the film thickness, those are the types of things that will limit the smallest size that you can make. But a tip can be quite sharp, and the aspect ratio can be quite sharp. So depending on the fracture mechanism of the material that you're studying, you might be able to make things that are smaller, maybe not as high throughput, but of course you can also have an array of probes, an array of tips, and do a little bit faster scale production. I'd say, I mean, focused ion beam is also a little bit low throughput. Okay, so in terms of tip-assisted studies in ferroelectrics, where a tip is used in some fashion to fabricate ferroelectric materials, in this case, there has been tip-assisted local crystallization, so not removing material, but a tip-assisted study. Here, a hole was created in a polymer, kind of as a stencil, and then the ferroelectric was grown on top. And in a nice example from the last couple of years from Brian Huey's group at University of Connecticut, they actually used tomographic AFM, so they were removing a layer at a time and reconstructing the PFM signal as a function of depth. So this is some really nice work. So what we started out by doing was trying to understand the parameter space. So we figured out we would measure things as a function of loading force, as a function of line separation to see, and tip velocity to see how quickly or how fast or how smoothly, how nicely we could remove material. So you can see as a function of loading force and as a function of line separation. And we can fit it to a model. We can measure the roughness. We can measure the depth, how much material was removed. I won't go into so much detail, but this data is published. And so we can measure it as a function of velocity, tip velocity as well. So what we were interested in was less about understanding the physics of the material removal process, but understanding what we would need to do if we wanted to remove X amount. So basically we could have a lookup table and say, okay, I want to make something that's this deep, or I want to remove something, that much material this quickly. And then we would know what parameters to use for this particular material. So generally we found that there was a smaller separation between adjacent lines, resulted in a larger depth as we might expect. The depth was relatively unaffected by different velocities in that range in particular. And the roughness was increasing with the increasing force and depth. So the more removed and the faster we tried to remove it, the rougher the surface was. And so if you want to do a tomographic type approach, you probably really want to do it a little bit slowly. You want to, in essence, operate in a polishing regime where you're just removing a little bit of material each time, which of course would be more time consuming, but then the surface would be much nicer for doing a PFM study. And we can measure current at the same time. Actually, for this film, we weren't sure what the thickness of the film was. And so we knew when we had reached the bottom electrode, because that's when we started measuring a current. And so we could identify that the film thickness was, in fact, 50 nanometers. And then we started exploring what happens instead of trying to thin a region. We wanted to carve or create a nanostructure. So first we wanted to understand the angle dependency. Maybe there would be something interesting in terms of carving particularly against or along a crystallographic axis or against a domain. And basically what we found was that, so this was a little bit time consuming. It's loading the sample and doing a scratch, taking it out, rotating it, putting it back in and doing another scratch and finding the same position in each case. But you can see that the thinnest line is always when the cantilever is in this direction. And you might expect that. So the torsion of the cantilever, even though this is somewhat of a high torsional stiffness lever, there is still a little bit of twist when you're going around that, that direction and that motion. So the 0 degree parallel to lever was the best angle for machining. And so we did our carving in that direction in each case. Again, we looked as a function of force, and here we're going up to micronewtons again as a function of tip velocity. So we figure out the thinnest line we can draw, the deepest line we can draw, and again, now we have the parameters that we need to be able to apply our machining. And so we tried to make the smallest nanostructure we thought we could make. This ended up being around 90 nanometers. We were pleased that we were able to still switch the material, so the switching could still happen. It was still ferroelectric after the machining process, so it didn't seem to damage the material. And we could also create a fabricated nano array, so we could do a little bit larger scale, and we could do arbitrary shapes. And this was actually a little bit surprising because this worked basically the first time. We just loaded a bitmap image, a binary image, and carved out this structure. And this is in one pass, so in less than a minute. The imaging took longer than the machining, and we think that's quite interesting. Then we tried to see if we could make a nanocapacitor array. So the metal, to remove the metal, to carve the metal was a little bit more challenging because it has different mechanical properties, of course, than the bismuth ferrite. But this is one of the better examples that we had where we didn't completely delaminate the top electrodes, but we were able to make individually addressable and switchable nanocapacitor array. You can see we switch it into a checkerboard pattern, and then we can switch it back. So we were happy with that result too. So in summary, we found that the application of a force via an AFM tip affected both the switching voltage and the current. We saw this increasing current with increasing force. The AFM-based machining can be used to fabricate a range of nanostructures. The ferroelectricity of the machined nano islands was retained. And we studied the machining as a function of depth and width to understand the parameters needed to make the structures that we were most interested in. And just as a general overview, so hopefully you're now a little bit more familiar with AFM and PFM than you were before, but you know that AFM is widely used for the characterization of functional materials. There are a range of modes that exist. Here we discussed electrical modes, mainly PFM, as well as a bit of nanomechanical machining. And PFM was originally developed to study ferroelectric materials, and its application has expanded to a wide range of materials. I didn't really talk about that. And the technical developments have been motivated by wanting to understand materials properties, but also differentiate between different contrast mechanisms and really prove that the PFM is the origin of the signal that you're measuring. And so just to finish, here's my group taken probably a year and a half ago. The funding for some of the work that we showed, so Science Foundation Ireland, the China Scholarship Council, University College Dublin. And just to highlight, if you are doing any work related to AFM, nanofabrication or nanolithography, we do have a call for papers in a Springer journal. And if you are interested, do contact me about that. And yeah, I'd be happy to answer any questions.
Thank you very much, Brian, for your nice presentation. So now we have time for a few questions.
Yeah, thank you, Brian, for such a nice and very comprehensive description of AFM. I'm Binay Kumar from Delhi University, India. I'm facing some problem, maybe experimental one. We are growing crystals of piezoelectric materials of various kind. Organic crystals whose D33 values are 5 or 10 picocoulomb per Newton, and on the other hand, very hard crystal, PM and PT, etc. But when we are going for the measurement of PFM, our operator who is handling the equipment says that our sample is not so good because the tips are getting damaged. And we do not have any combination of things, either voltage or way of measurement to perform this experiment. Can you suggest where the mistake is going on, that this system is not very suitable while he was able to do the work on thin films, but in single crystals, he's saying it is because very hard or something, so it cannot be done. Can you give some suggestion on this?
Yeah, I'm not entirely sure, but you're describing it as being very hard, and maybe what you can do then is use a very stiff lever, one that will be very wear resistant. Maybe what's happening since it's so hard is that the conducting coating is wearing off very quickly. If it's a crystal, maybe you can get away with applying a much larger voltage than you would normally apply with a thin film. But maybe these conducting diamond probes can be of use, just to just to show. So the conducting diamond probes that we use, you can use for PFM as well as for conducting measurements. And even after doing all of the machining that I showed, the tip radius didn't change very much. So the single crystal diamond probes are very wear resistant. And if your issue is related somehow to the tip damage owing to this, the hard properties of the crystal you're studying, then maybe a more suitable tip would help. But I'm not sure.
Okay, thank you. So one suggestion is related to the quality of tips and maybe the combination of current and voltage which we are using for this. This may be the reason. Okay, thank you for your suggestion.
Yep.
Thank you very much. We have time for another question.
Okay.
Yeah, Igor.
As I understand, you use diamond for all your measurement. You use diamond cantilever, yes? Diamond tip. Or...
Yeah, I think not for all of the measurements, just mainly for the machining measurements. But still, for some of the PFM and electrical measurements, we tend to prefer using platinum coated, for instance.
But you say this is single diamond or it's covered in diamond?
The probes we're using for the machining is a single crystal diamond,
but
and doped.
But who produced this? What is the price? Because what is company?
I don't want to advertise particularly for a company, but the name is Adama Innovations.
What is price of this? Because this is single diamond. This is very expensive. Yes.
Yeah, they're more expensive. Maybe on the order of 150 euros per probe.
Yes, yes, I believe.
But there is a picture here from the company. So Adama Innovations is the name.
But only one company produced it.
Well, I think other companies as well, and other manufacturers or other vendors have sold diamond probes.
Diamond must be conductive diamond. Yes.
For doing PFM or conducting AFM, yeah, you need to use a conducting diamond.
Brian, can you tell me what is this? These are crystals in which the Nature 565 left-hand side top picture. These are some crystals on which the work has been done?
No, sorry, that's an architectural discovery in China from 2019, I believe. So some early tools for cutting. Early human history tools for cutting.
Yeah.
So we've come a long way, maybe.
So
I also have a question about the nanomachining. So when you do these structures, so you obviously have to drag this material out when you're doing the nanomachining. So you don't see that it goes preferentially to the edges of these, for example, columns that you're doing, or it just goes to the side of the sample?
Yeah, no, it's a very good question, and maybe you briefly saw something that I showed. So the company claims that they've done some work to design the shape of the probe to cause material to move up the apex of the tip and away from the apex. It depends completely on the material that you're studying. But what I didn't show was that after machining, this is what it looks like. So the material is still there.
Okay, yeah.
So it gets pushed away. So what we have as a routine is after we do the machining, we do a cleaning step. And it's just a low force imaging. And that's shown here. So this is after cleaning. where it's not taking the sample out and rinsing it or sonicating it or anything. It's just scraping it again with the AFM tip. And then it pushes that to the side.
All right. So in terms of the resolution, you said that the minimum size you could do is 90 nanometers, right?
Yeah, that's the minimum size that we were able to draw just to carve out a material. And so it depends whether or not you want to have an isolated structure and what the thickness of the film is. So this, you know, if the tip goes down really far, then the aspect ratio is going to define or limit in a way what size, how close you can draw two lines. But what we found with the bismuth ferrite that we studied was that the trench that we draw is wider than the apex of the tip. So we can do the tip reconstruction as I showed. We can place the reconstructed apex in the trench that we draw. And so what's happening is that actually we're fracturing the material and a larger region is breaking at the speed or force that we're doing our measurement. So it depends on the fracture, on the mechanics of the material that you're studying. A different material or with a slightly different force or pressure with different mechanical properties might create a sharper trench or line. But we're always going to be limited by the aspect ratio of the probe and how deep the material is if you want to make an isolated nanostructure.
Okay, thank you very much. And thanks for the presentation, it was really nice.
Thank you.
So thank you very much, Brian.